Hi, and thank you for joining us for this webinar. I'm the product manager at Horizon Discovery for the diagnostics division. What I'm going to do is give you a little bit of a flavour of what we do at Horizon Discovery, and then walk through and talk about the FISH and IHC standards. So Horizon Discovery is a genomic translational company, and we have business units that cover gene editing, discovery services, target identification and validation, as well as, and this is the unit that I'm responsible for, the diagnostic reagents. Now, one question that we always ask ourselves and ask other people in our labs, and have started to really push and ask pathology labs, whether it be molecular pathologists or histopathologists or cytogeneticists, is how do you know that your assay is working today? Now, the most common results that we get from that question is, well, the positive control that you're using in the kits gives you the expected result, or the negative result, the negative control that you're using gives you the expected result, and that's all good. The next questions we ask ourselves, and we start to ask you guys, is, well, what are the controls that you're using, where are they from, and what's their suitability and how they validated? One of the most worrying things for me when I've asked these questions is that often the negative result, certainly in molecular diagnostic assays, can be just water, and so completely non-representative of a patient sample. And likewise, with positive control for molecular assay, it's often a short primer that will be, is always easy to amplify. For FISH or IHC, occasionally the positive control can be so overexpressed, or such high copy number that any probe will work for it, and again isn't patient relevant or patient suitable. Now, when you go through the workflow, I've got a very simple schematic here where you have the tumor sample. It may go off to histology, it may go off for cytogenetics analysis, it may go down to genotyping, and then you have diagnosis. So each of these steps, there's the opportunity of variability to creep in. You've got sample quality, sample heterogeneity. When you've got the tumor, is the boundary of the tumor, does that show the same characteristics as, say, the center of the tumor? Does it vary throughout the tumor when you're looking at IHC slides or FISH slides? The antibody that you're using for IHC will make a big impact on how sensitive your assay is and how you score. You've then got for cytogenetics and running FISH the probe choice. Which supplier do you use for your probe? Which probe do you use from a supplier? Because some suppliers will have maybe 3 or 4 different options. And then the final, which is sometimes forgotten, is the characteristics of the mutation that you're looking at. So a good example is the EML4-ALK translocation, which is a relatively new diagnostic test. If you're looking at FISH, are the probes that you're using covering all of the variants that have currently been identified? And if they are covering all the variants, which ones are you able to then distinguish which ones are clinically relevant if they are all clinically relevant? Now, this is another a nice slide to summarize very much how you pick which tests you may choose to do depending on the mutations you're looking for. Typically, rare mutations of SNPs or small deletions would be genotyped in a molecular diagnostic laboratory. For much larger chromosomal abnormalities, so say gene copy number variation or large deletions or translocations, would then either be tested using cytogenetics or histology. Now, as I'm going to be talking a lot about IHC and FISH, I thought it would be good at the start just to highlight the differences between the assays and maybe some of the challenges that you face either running IHC or running FISH. Now, from this table, it's easy to see. So with FISH, as you know, you're looking at the genetic abnormality. IHC, you're looking at the protein expression. And there's argument that protein expression is a much more attractive property to be looking at than, say, the genetic abnormality. In terms of choosing a probe or an antibody for testing, I'd say for both IHC or FISH, it can be difficult. Even for the very well-established assays, so for HER2 testing, you've already got 3 or 4 suppliers that have HER2 as an IHC test or as a FISH test. So how do you choose that, and how do you know that assay is working in your hands and it's the best one for you to be using? IHC, I'd say, is easier and simpler to set up, but then the scoring is much more difficult. So you do need a much keener eye and a much more experienced eye to actually subjectively score what you're looking at. And FISH is the other way around, where it's much more difficult to set up initially, but once it's set up, the scoring is much more binary. You can see, it's much more yes or no. Now, IHC then has the benefit that it's more cost efficient and will give you a faster result. Now, different labs, choose IHC or FISH, or you do the screening with IHC followed by FISH. For us, it's not so much how you apply. It's more how do you know that if you are using IHC, it's working today, or if you are using FISH, the assay is working for you. Now, as you all know, tumor samples show a high degree of heterogeneity, and so depending on which section you get from a tumor may actually govern how efficient your test is due to morphological or epigenetic changes, and different tumor cell clones will diverge as the tumor grows and develops. And depending on the method you're using, you may be able to have a limit detection down to 10% or 50% or 100%. With FISH or IHC, the nice thing is that you actually you can see the slide, you can see the stain, you can normally see how well your method has worked. For molecular diagnostics, which we're not really going to touch on today, it's much more difficult to know and understand the limit of detection. So if you consider the variability that can sneak in during the process, and this is very much, it can sometimes be out of your control as well. So, for example, the sample quality is key to either FISH or IHC. The sample, some of you may or may not know whether your sample has been treated in formalin for 1 hour or 4 hours or 24 hours. You don't know once it's been treated, has it then been sat on the side, or has it been vacuum packed? Has it been stored at room temperature? Has it been stored at 4 degrees? All of these variables will come together to impact on the quality of your sample. And certainly for IHC, that would then impact on whether or not you get efficient antigen retrieval and then get a good stain using your antibody. Likewise for FISH, this may impact on background or non-specific staining. And if you're setting up a new assay where you're not actually sure you've got a positive result, non-specific staining for either IHC or FISH can be a real problem, because when do you know when a false positive isn't actually a real positive? And without reference slides to help you along the way, you could be using a lot of your precious patient samples trying to understand and get an assay up and running and optimized. I thought it would be good to take HER2 as an example, because it's a very well-established test. It uses both IHC and FISH. And the accepted guidelines are that you'd take the tumor sample that was from breast tissue. You'd then test it using IHC. You'd score it from 0 to 3+. Anything that's 0 or 1+ would then be considered negative. If it's a 2+, it will be equivocal, and so it would then go through down to HER2 FISH testing. If the FISH test came out as a positive result, it would then be recommended for consideration for Herceptin treatment. If the IHC is strikingly positive, so 3+, it would also be considered for Herceptin straight away. Now, what I've got on the next two slides is the challenges that I see for either IHC or fish. IHC, as I mentioned briefly, is very subjective, particularly for around the boundaries. So the difference between, it's not easy to see on this slide, but the difference between a 1+ score and a 2+ score. This would be a negative. This would then be considered for fish testing. Without an experienced eye or experienced lab, these decisions can be very difficult to make, and could actually be, this is where error could sneak in. With the availability of reference slides, these types of decisions can become much more obvious and much clearer to make. If you do want to see these slides in more detail, this has come straight from the DACO manual, so you can actually you can see much higher resolution for your use. And then for fish, like I said before, I think with fish it's more difficult to get fish set up initially, but once it's set up, the scoring is much simpler because it's in my eyes it's more binary. The only time when scoring can start to become difficult is when you have either nuclei that are overlapping, like here, or you have the nuclei isn't fully visible, and then you have to start not counting those cells. But in both, I mean, I didn't mention the last slide, but in both fish and IHC, the sample quality can really make an impact on how easy it is to actually look at these particular mutations. And what they thought what's been achieved what's been applied and achieved in some way to standardize HER2 testing is bringing in the control slides. And so if you're running an IHC test, the control slides have to be included in every run, and the actual result has to match the predicted result. So if you're looking at the 1+ control cell line and you get a 1+, that run is acceptable. If the 1+ doesn't come out as 1+, then you need to throw away all of the data from that run and run it again, maybe getting in a new kit or a new antibody. And the results require both proportion and intensity measurements. And what I'd like to say, and it's my real feeling, is that by bringing in the reference slides, we've been able to standardize how HER2 testing is being applied. And that's a very good time for me to introduce what we believe is a reference standard. So for us, it's an independent, externally validated reference tool. It will allow you to understand the sensitivity and limits detection of your assay. It allows you to monitor the reproducibility of your molecular assay, and they are absolutely critical for the development and quality control of your assays. And this is because they enable you to start testing new assays, or if you're switching from, say, one probe to a different probe, you can test using the reference standards before having to then test using clinical samples. And this is a very useful tool for when you've got rare mutations. EML4-ALK, some labs may only see 5 to 10 positive results in a given year, and to have to wait or to have to use those samples to then set up the assay is a big challenge. So if you can set up the assay and get the assay close to fully optimized and fully validated with reference material, it then allows you that when you can get your hands on positive material, you can do the final validation with that positive material. And I think it's what the question I had at the very start is, how do you know that your assay is working today? Reference standards will tell you if they're run every single batch. The next part of the talk, I'm going to focus a little bit more on the technology that we have at Horizon, and then try and, I guess, in some ways stimulate thoughts at your end of how we can apply the technology to develop further fish slides or IHC reference slides. We've we've made a big progress and developed a lot of reference standards, and I'm going to show them the next couple of slides for molecular assays. And over the last 9 to 12 months, we've started to move more into the IHC and the fish world, as it were. And we have some good ideas. We've had some successes, but I think for us it's critical that we get feedback from you guys, and also develop partnerships and collaborations so that we know where to go. Especially for a lot of these new translocations that are coming out, we are essentially going to be together setting the scene of how these should be tested moving forward, and almost setting guidelines for the best way of testing for these mutations. So coming back to this slide, what we have at Horizon is we have the gene editing platform Genesis. So what we do is we take what would be considered a wild-type cell line, from traditional sources like ATCC or wherever. We take that and then do a single-cell dilution, simply because every single cell line that we get from external sources is heterogeneous. And so by single-cell diluting, we then create a clonal wild-type cell line where we know that every single cell within that clonal population is close to identical. We then take that and use our Genesis gene editing technology to then generate our clonal mutant cell line. This again, once we've generated this, you would go to a single cell dilution step as well to ensure that the mutant cell line is clonal. And at both these steps, these cell lines go through full cell line validation. Now the validation we do is very intensive, so we do STR profiling and SNP6 to ensure the cell line we have is what it should be. We then confirm the integration at the endogenous loci of the mutation using DNA and DNA locus-specific PCR. We used digital PCR or traditional cDNA PCR to look at the expression of the allele. And also we can use our digital PCR platform to confirm the clonality as well as the gene copy number. And I think the most important part, or the most important bit of information on this slide, is that at the end point of our engineering is that we have a clonal mutant cell line and a clonal wild-type cell line that are essentially identical except for that one mutation that has been incorporated. And that is as close to patient genetics as you can get as a model system. Now, some of the other half of our company uses this for functional analysis. What we've done is taken the mutant and the wild-type cell lines to develop reference standards, and we've done this in different flavors. So we have genomic DNA, either wild-type or mutant on their own, or wild-type and mutant mixed together, either as singleplex or multiplex. We've generated FFP blocks using the cell lines. We've generated FFP xenograft blocks, so we've taken a cell line, injected them into the mouse, and grown a xenograft from there. We've then taken FFP sections either from the xenograft blocks or the cell line blocks, and likewise we've now started to sort of move really into this area where we generate cell slides either in the FFP format or cell format or metaphase on request. And depending on the reference standard that we generate will then govern which type of validation we go to, whether it's Sanger sequencing, digital PCR, RT-PCR fish, or IHC. And for the molecular offering that we have, we've got a very extensive catalogue now where we're covering a lot of the main targets like BRAF, AKT1, the KRAS, EGFR, NRAS, and we're now starting to move into the fish and IHC and looking to expand a similar size catalogue for that. Now, what we believe, and what I'm going to show in the next few slides, is that with all the technology we have and the experience we have in generating the FFP blocks and FFP xenografts, we can very easily, and actually we've got some sort of internal data supporting this, very easily generate a IHC slide which will have a variant proportional score. I think that's relatively simple. with IHC, there's obviously lots of different scoring paradigms, and one of them is an intensity score, where this is seen for her too as well. And the intensity score is much more difficult to replicate because the biology behind it. It's not just editing at the gene level. It's somehow editing or controlling at the RNA expression or even the protein expression level. So for the proportional score, like I said, it's relatively simple. We take a mutant that we've generated, so like a EML4 out translocation mutant. We can then mix that with the wild type that was used to generate mutant, and then create a reference slide from that using our FFPE processing technology that we have. What's really nice with our FFPE technology is its consistency. So here we have 8 different FFPE blocks where we've taken sections, random sections from the blocks, and we're able to control the exact number of cells per block, which is very important for moving into IHC in fish, where we want to ensure that if you're doing accounting, then your field of view will always be similar. So if you always want to look at hundreds, if you want to say look for 50 positives within 100, or you're looking at 20 positives within 100, the consistency and the homogeneity of our blocks and sections will always remain the same. We go one step further as well, because obviously H&E is always subjective to the eye, so we try and make it objective. So what we do is extract the DNA and check that the DNA lies between the boundaries of 550 and 750 nanograms to ensure that the sections consistently have the same DNA content, and then we apply that to cell content. We also, and this is probably one of the neatest bits of kit that we ever brought into the lab, is the digital PCR equipment. And what digital PCR allows you to do is count the allele burden of any given sample down to an accuracy of, we're down to about 0.1% accuracy. And so what we've been able to do is take the mutant cell lines and the wild type cell lines, mix them to a defined allelic frequency, so say 25%. Once we've mixed them, we then fix them in fix them in formalin, put them into a FFPE block with paraffin embedding, and then we've taken sections from throughout the block, so it's start, middle, and end. And as you can see, the block shows 25% mutation all the way through the block. Likewise, we've generated a 5% mutation block. Again, that comes out slightly higher than 5, but it's within the expected range. And then we've also got as low as a 1% mutation. We can also, with the digital PCR, and it's always tricky when I start writing talks not to start just selling the digital PCR machine, but it is a very flexible system. And so what else you can do with digital PCR is actually look at copy number analysis or copy number assays. And so, for example, with an EGFR project that we have ongoing, we've been able to identify 3 different cell lines where we have varying numbers of EGFR, and this is a very useful tool for us prior to applying them for fish standards, because if you can define what's going on at the genetic level using non-fish methods, it gives you great confidence that when you're setting things up with fish, that what you're seeing is exactly what you should be seeing. And this is sort of a small list of where we've focused on initially for our fish slides, and the different translocations and one deletion of P10. Obviously, one of the most interesting is the EML4 ALK translocation that we have, and also the corresponding mutation, the ROS1 translocation. What we've done is the mutations that are typically found in solid tumors, we've made them as FFPE reference slides, and the ones that are found as liquid, we put them as interface spreads, or on request we can make metaphase spreads of those as well. And we started to test a number of different probes from different manufacturers, and this is it's highlighted for us. And I haven't been able to show all the data. But it's highlighted to us that using different probes, you certainly need to use different methods and different protocols. Because if you have one standard protocol and you use, say, a probe from Empire Genomics, a probe from Cytocell, a probe from Abbott, a probe from Createch, the signal, the performance of those probes will vary greatly. We found that you can optimize every single probe, but technically you have to optimize your assay to make sure those probes are working. And so, if you have reference slides and you can optimize your technique with reference slides, it then will give you great confidence that you can then apply those probes to your clinical samples, and then you rather than spending or almost wasting your precious patient material on setting up assays and testing assays, you can do a lot of that sort of research and development work using reference slides. It's especially important, actually, I should add, it's especially important when you're working with mutations that are so rare that you may only see a handful of positive results each year. And these are some other slides from our, so we've got the ML, ENL, and the RUNX X1. Here you're looking at, we've got slightly better images on our website if you want to look, but here you're looking at, and my laser pointer is actually bigger than the cell. So here's the fusion. Here's the fusion. So this is the breaker parts. That's a normal, and then you've got the breaker parts of ML and ENL in the red and the green. And it's the opposite for the RUNX X1, RUNX XT1 dual fusion, where you're looking at a green and a red would be normal, and then when they come together, you've got the fusion. So how we're looking at, or how we would suggest that you can use reference slides is certainly at the stage of evaluating probes, or even if you're looking at switching between suppliers. So you have reference material to then, does my probe work with this slide? Yes, it does. Okay, we'll bring in another probe, and then we can test it again. And I think, and this is possibly will become much more important, is the daily process monitoring, so ensure that your probe is working on the day of the test, and make sure that what you're seeing is not background or non-specific staining. I was talking to a number of pathologists last week, and they were saying that with the EML fallout testing, because they don't see positive samples that often, they always worry that the probe may have gone off, and so without actually having a positive slide to run each time you run the test, you don't necessarily know if the probe is always working. Then moving on, and this is more speculative at this point, into the intensity score reference standards. So where we're looking at generating low expressor mutants, medium expressor mutants, and high expressors. So then we can generate intensity scores of say 0 to 3. We've had some success. So we now have an EML4ALK IHC slide that shows what we would class somewhere between medium high to high expressor, using the antibody from Ventana. What this has done, certainly internally here, is opened a bit of a can of worms, because we're using this as a baseline to then generate additional cell lines that will have different gene expressions. Because the out testing for IHC is so new, it's difficult to know what a strong expressor is versus a medium. And if you use one antibody, one antibody comes out as a low expressor, could actually then be seen as a high using a different antibody. And so at this point, by having the reference standard, we can start to answer that question, and it will really help moving forward. And I think So what we plan to do is get reference slides, look to identify low, medium, and high, and then we can start doing antibody comparisons. What I would say is definitely an opportunity for you guys who are running this test or running, maybe not the ALK test, but if you're running other IHC, is if there are no guidelines right now, you can if you start to use reference slides at this point, you can then start to gather information about the test that you're running. So, for example, this is a completely theoretical example, but if we stay with the ALK story, if say with the ALK expression, maybe ALK expression where if you've got a 1+ score with ALK, you respond really well to crizotinib. If you then have an ALK expression at a 3+, the response maybe is poorer, so you don't respond as well, and maybe you don't respond at all. And so, if by knowing that you've got a 1+ and a 3+ at this point, when it comes to then evaluating or analysing the treatment or successive treatment, you can then apply it back to the test. And unless you've got a reference down at this point and a reference slide at this point in your test, you won't have any way of benchmarking really what you've seen. And so although it's not essential for, say, the ALK to have reference slides in now, by having a reference slide, you'll be able to retrospectively then use the data from post-treatment to work out the success of it, and maybe then help to personalize the treatment moving forward. And so this, I've summarized in a similar way to the fish of how how you could use reference slides. So very much for antibody evaluation. Who do you get your antibody from? Which clones you choose? Which ones work using your standard protocol? And also for the daily process monitoring. So ensure that the tissue is being processed correctly. Ensure the tumor sample is being treated as delicately as possible, and that you're able to perform antigen retrieval for good staining. Now, at Horizon Diagnostics, we've worked very closely with a lot of the proficiency scheme organisers, both in Europe and the US. We're continuing to do that, and we are looking to really push the standardisation of FISH and IHC through these proficiency schemes. We're also working at the lab level as well as the cancer centre level, and talking to the likes of the FDA and also the EMEA to really try and standardise all of these diagnostic tests. At the end of the day, for us, and this is a slide we sometimes put at the start, but I often put it at the end. For us, every person in our company has in some way been touched by cancer, unfortunately, whether it's a colleague or a friend or a family member. And what we want to do as a team is ensure that anyone that is being tested in the future, if they do have cancer, if they are being tested in the future, is to ensure that the molecular diagnostic test they're having, or the IHC test, or the FISH test they have, is as accurate as it can be, and no mistakes are made, because you require an accurate test to then get an accurate treatment, especially as personalized medicine becomes more and more personalized. And so and as you get better testing and better treatment, you will eventually get better patient outcomes. So I'd like to thank you very much for your time and listening to my talk.